Hello. Hi. I'm a PhD student at the University of Chicago, and I'm going to be presenting our work goal supporting general and dynamic adaptation in computing systems. This work was done in collaboration with researchers from Rice University. All right. We begin by motivating the need for adaptation in real world systems. Consider a CCTV camera connected to a line power, which is consuming scenes in from its surrounding and compressing them into a video using a video encoder that is running on some embedded hardware. The compressed video is then forwarded to a user. Such systems often need to meet a quality of service requirement that is defined by the user as a high level goal on the metrics of the system. For example, in this case, the user might want the camera to produce a steady stream of frames at 30 frames per second while maximizing quality. Choosing appropriate configurations is important because input scenes have significant impact on the performance characteristics of the system. For example, if the scene is high frequency, or in other words, has high variance, the encoder will need to do a lot of computation to find redundancies between frames while compressing them, and vice versa. One could potentially achieve the desired behavior by carefully configuring the entire system based on some example input scenes. However, because the environment of the camera is dynamic, the scenes change dynamically. And when the scenes change, the configurations that were close to optimal for a particular type of input scene will no longer be valid. As we can see in this chart, the system produces frames at a steady 30 frames per second during the initial part of the execution, when the input frames closely resemble the testing frames that were used during deployment. However, at frame 500, the scene changes dramatically and the throughput changes along with it. This results in a loss of quality of service. Hence, based on these observations, we can safely say that adaptation is important because no single configuration is optimal for the entire execution of the system. And as we will see later, this kind of pattern is followed by several different applications, ranging from those running on cloud to those running on embedded systems. In fact, it is very unlikely that one can find a single configuration that is optimal for the entire execution of most, if not all, systems. Hopefully, by now we've motivated the need for adaptation, and we're going to look at the support that is provided by prior work for implementing adaptation in applications. The very nature of the systems that need to implement provide us a good outline for solving the problem of adaptation. The execution of these systems can be broken down into four distinct phases. First, we have the system itself that executes using its myriad of configurations. To adapt the system, we continually monitor it and then use this information to analyze its behavior to determine if we are successfully meeting the goal. Finally, based on this analysis, we plan about how to execute the application for the following window to ensure that the application continues to meet the required goal. This provides us with a clean template for adding adaptation to these systems. This template itself is divided into two parts. The first is composed of the system execution and monitoring. We call this the adaptation specification. This contains the details of adaptation. For example, in the case of the CCTV system, it contains the goal that needs to be met and the knobs that can be actuated to meet the goal. These knobs can be these knobs can exist at any level in the system. For example, the video encoder has these knobs that can determine how hard the encoder will work and which algorithms it will use to find redundancies between frames. Similarly, hardware knobs are ones that people would expect, like the number of cores used and the core frequency and the on-core frequency. The second part of the template the second part of the template consists of a component that consumes the feedback to produce an execution plan. We call this the adaptation logic. The adaptation logic is responsible for making principal decisions about the values to use for the knobs such that the application meets the goal defined in the adaptation specification. Prior work packages the adaptations logic into a language or a library runtime, which is initialized using the adaptation specification, as it tells the adaptation logic what goal needs to be achieved and what knobs can be actuated to that end. However, to the best of our knowledge, all prior works are implemented to support a narrow set of adaptation specifications. For example, POET was developed to allow systems to meet a throughput constraint while minimizing energy using only hardware knobs. It cannot actuate application knobs, and it cannot support any other goal. Similarly, NES only supports actuating application level knobs to meet a quality constraint while minimizing energy. So, as one would expect, this severely limits the scenarios in which prior works can be used. For example, ignoring the knobs and considering only the goal, a developer may choose an appropriate framework to support the maximizing quality goal that we mentioned earlier. But if in a different deployment, the CCTV is deployed with a battery that is periodically recharged, the goal might change to minimizing energy to ensure that no data is lost. So we need to maintain two different versions of the same fundamental system with two completely different dependencies. Things might be even more complicated as they often are in the real world. For example, the CCTV camera may be connected to both line power and battery power, and it needs to and it switches to battery power when the line power goes out. And in this case, the system would need to dynamically modify the adaptation specification to meet the requirements. We call this ability to dynamically modify adaptation specifications meta adaptation. And this brings us to our second observation. Just as adaptation is necessary because there is no single optimal configuration for the entire execution, there is no single optimal adaptation specification that is optimal for the entire execution either. Hence, we need meta adaptation. Meta adaptation cannot, to the best of our knowledge, be supported by any existing framework because they are inherently developed to support a narrow set of adaptation specifications. Having looked at prior work and its limitations, we'll now go over the goal adaptation framework and try to understand how it overcomes the limitations of prior work. So, Goal, which stands for Goal Oriented Adaptation Language, is implemented as an extension of the Swift programming language. The best way to understand Goal is by walking through an example of how Goal may be used to add adaptation to the application. Here we have a simplified version of the CCTV example that we've been discussing. First, in this original code, we first initialize the encoder, initialize the knobs, which are QP and ME here, and continually encode input frames and record the quality. And this is how one would use goal to add adaptation to this example. We simply identify and declare knobs using types provided by goal. We use the optimize loop construct to identify the piece of code that needs to be adapted, and we report the quality as feedback using the measure function that is provided by goal. These are the only changes that need to be performed in the source code of the application. Finally, the developer writes an adaptation specification in a DSL provided by goal, which is compiled just in time at the time of the execution of the application. Each section in the adaptation specification corresponds to changes being made in the code. We identify the control loop for which the adaptation specification is defined and define the goal for it. We identify the metrics that are going to be used as feedback. Some of them are provided explicitly by the application using the measure function, for example, quality here, and others are recorded implicitly by the goal framework. For example, it can easily compute throughput by counting the number of iterations per second, and energy can be read from the underlying hardware. Finally, we identify the knobs along with their allowed values. And a developer may optionally provide additional conditions on how the knobs should be set. For example, here we say that the product of the number of cores and core frequency should always be greater than 2400. As the application is executing, the goal runtime reads the metrics that are provided by the application using the measure function, and it passes the metrics that are relevant to the current goal of the application to an adaptive time varying virtualized adaptation logic that produces a schedule of knob configurations based on a model obtained using goals model builder. The model builder is also provided as a facility in goal, but more details for the model builder can be found in the paper. After every iteration, the goal runtime sets the knob configurations for both the application and the system defined in the adaptation specifications to ensure that the application meets the goal on average during a user-defined window. The changes that we made to the code thus far are enough to implement both versions of the CCTV camera that we mentioned earlier. The programmer only needs to modify the goal that was defined in the DSL without even having to recompile the binary. However, Goal provides several facilities to modify all aspects of the adaptation specification dynamically as first-class programming objects. For the purposes of this talk, we only discuss the intent function that allows applications to dynamically modify the goal of the application. As we can see here, the developer just adds a conditional statement that calls the intent function to switch to maximize quality goal when direct power is available. Otherwise, it calls the intent function to switch to the minimize energy goal when system is being powered by the battery. In this way, we are effectively allowing the application to continually provide an updated view of the adaptation specifications to the framework based on its current requirements. This chart shows a time series execution of the application. It shows the execution of a version that uses prior work that cannot support meta adaptation, and it shows a version using Goal that performs meta adaptation. The execution starts when line power is available, so both versions try to produce maximum quality of 55 PSNR. Then at frame 650, the power goes out and the camera switches to battery power. Here, only the goal version is able to change its goal dynamically. As we can see, the quality decreases to 45 PSNR and the power consumption decreases accordingly. The green region in the chart shows the improvement in power consumption between the adaptation, the prior work version and the goal version. Right. Now that we've looked at how we can use Goal to implement adaptation, we're going to take a quick look at the evaluation of the Goal framework. We evaluate Goal on 7 real-world applications running on both embedded and server systems. These applications completely utilize all the resources available on the underlying hardware and have their own application-specific goals and meta-adaptation requirements. Furthermore, the set of knobs that are used by all of these applications are unique. This chart shows Goal's abilities to reliably meet the adaptation specification of an application. The y-axis shows the mean absolute percentage error. The high error of the linear controller shows that all applications exhibit nonlinear behavior. So any adaptation logic that hopes to provide reliable behavior needs to support nonlinear performance characteristics. Our evaluation shows that using our framework, applications can meet their goal with as low an error as a version of the application that uses a specifically synthesized adaptation logic. However, the benefits can be seen when applications need to perform meta-adaptations as shown here. The y-axis shows performance improvement in terms of the metric that becomes important after meta-adaptation. For example, in the CCTV application, energy becomes important after meta-adaptation was performed. The improvements are normalized to oracles for each application. We find that Goal provides a 1.69 times improvement in each application's relevant metrics after meta-adaptation is performed. This provides a clear advantage over existing works that cannot support meta-adaptations due to their inherent limitations. Similarly, since meta-adaptation is done dynamically, we find that the number of iterations required to converge to the new adaptation specifications after meta-adaptation is done is almost half of what would be required if the application were to perform ad hoc meta-adaptation using multiple adaptation logics. This is because the ad hoc setup would need to dynamically construct and deconstruct adaptation logics whenever it needed to perform meta-adaptation, incurring significant overhead. Finally, we see that adding interfaces for an integration for multiple different adaptation logics for ad hoc meta adaptation in a single application significantly increases the amount of code, thus making the system hard to maintain. However, using Goal, we require only half the modifications that would be required for this ad hoc meta adaptation implementation. And this includes the lines for the adaptation specification. So the actual lines that we need to modify in the source code itself are even fewer. Now, to sum up the talk, um, we have tried to motivate adaptation. We have tried to motivate and discuss how adaptation is important because there is no single configuration that is optimal for the entire execution. And meta adaptation is required due to the observation that just as no single configuration is optimal for the entire execution, there is no single adaptation specification that is optimal for the entire execution. And existing works alleviate the job of building adaptation adaptive applications by packaging specialized knowledge and easing development of these adaptive control loops. However, they support a narrow range of metrics and knobs, and hence cannot support meta adaptation. Goal is and we implement Goal, a novel adaptation language and framework for generalized adaptation and meta adaptation that is backed by a virtualized time variant adaptive adaptation logic. And Goal provides a domain specific language for expressive adaptation specification declaration that are compiled just in time right before the application is about to execute and can be continually updated using constructs provided by fast for meta using constructs provided by Goal for meta adaptation. Finally, we evaluate Goal with 7 different adaptive applications and show that we can obtain a potentially 1.69 times performance improvement when meta adaptation is required by the application. Thank you.
All right.
Thank you for your talk. For me, it's not totally clear what is the principal difference between regular adaptation and meta adaptation. You switch specifications, but that is a strategy to achieve a more higher level goal. And is there a way to really pinpoint the difference between those concepts?
Yeah, so basically, at a high level, you're absolutely correct that supporting that adaptation meta adaptation is just a higher level of adaptation, just as you described. However, the problem is that most of the existing adaptation frameworks were defined for very specific problems, and so they know exactly the knobs that they're going to act upon and the goal that is going to be that the application is going to require them to meet. And so this inherently limits their ability to support a wide range of goals and knobs, right? So what meta adaptation allows the framework to do is that we can effectively, while the application is executing, change all aspects of adaptation. So this includes the goal that is being met, along with even the knobs that are being modified. So this is kind of we're completely changing the course of adaptation itself during execution. Does that make sense?
Okay, so to summarize, you allow like the object program that you're monitoring to guide or to define the things that you're adapting to, the goal that you're adapting for. Is that a good summary?
Yes, that is absolutely correct. Yes.
Okay, thank you. Then it's clear.
Maybe just to pick up on the general question. So out of the whole area of aspect-oriented programming, I think the one thing that came out of that is called context-oriented programming. And I think some people worked in the direction of context-based adaptation. And at least for me, without being too much in that area, it sounds very similar to your meta adaptation. Do you have any thoughts on that?
Yeah, so to the best of my knowledge, a lot of these frameworks that provide context-based adaptation, they provide this adaptation that is based on the functionality and not really on providing reliable behavior for a particular application. If I'm not mistaken on that, and please correct me if I am. So basically, what meta adaptation or this goal-oriented programming as we define it, does is that it allows, while maintaining the same functionality, it allows us to provide reliable behavior within that functionality. Does that make sense? So effectively, we're trying to maintain, we're trying to provide, let's say, reliable throughput or latency while the application is executing in the face of changing operating conditions and workloads.
As I said, I'm not entirely in that area. One author coming to mind is, I believe, Nicola Cardoso, and I think they also used very similar examples. So might just be worth a second look at that related work.
Yeah,
but I'm not. Do we have any other questions? Any questions from online? All right. Let's thank sorry. Let's thank Asan again